Hello, amazing people, students, lovers of chemistry, subscribers, and everyone out there. I'm super excited to start yet another series with you people on this space. My name is David, and all I do here is to take the mystery, you know it, out of chemistry so chemi can make history. All right, today we're starting a new series on the concept of gas laws. Now, this is one concept that has been taught in chemistry basically in secondary schools, and it has proven to be a hard nut to crack. So I thought, let's give it a go and let's see if we can break down the complexity and make it more assimilable for students to grasp. So without wasting any time or any further ado, let's get into what we have for today's video. First of all, we need to understand the basics. And to start off, we want to know what a gas is. So first question to answer in this case is, what is a gas? First things first, a gas is one of the three main states of matter. There are three main states of matter. We have the solid, we have the liquid, and we have the gas. Today we're looking at the gas, okay? And the gas, okay, the other two are the solids and liquids. In a gas state of matter, in a gaseous state of matter, the particles that make up a gas are very far apart and they move around freely in all directions. This is why gases can easily spread out and can fill any container that they are placed in. As we proceed, we're going to be seeing many characteristics of gases and why they behave the way they do. So I'd like you to stick around and enjoy every bit of today's lesson as we proceed. So now that we've understood what a gas is, let's move into some of the characteristics of a gas. Now, there are some things that make a gas special and that differentiate it from the other classes of matter. The first thing about gases is that gases have no fixed shape. Okay, there is no fixed shape you can assign to a gas. You cannot say a gas is square, a gas is circular, a gas is spherical. No, you can't assign that characteristic to a gas because gases take the shape of the container that they are placed in. They are very flexible. For instance, if you blow air into a balloon, it takes the shape of the balloon. Now here I have three illustrations. You can see some balloons on this place and they have the shape of a heart. They are heart shaped, and the gases that have been blown into them took the shape of the balloons, making the balloons to be inflated. Over here you can see the balloons have more like an oval spherical kind of shape, and the gases that filled them up took up the shapes of the balloons that they were placed in. And in the same case, we have a tire tube here or a rubber tube over here. The rubber tube here has the shape of a donut, and the gases that were used to fill up this tube took up the shape of the tube. So that confirms this characteristic of a gas, that a gas has no fixed shape assigned to it. It takes up the shape of the container that it is placed in. Now, gases have no fixed shape. The next characteristics of gases is that they have no fixed volume. Gases have no fixed volume assigned to them. What do we mean when we say gases have no fixed volume? We mean that they expand to fill all the space that is available to them, which is why when you spray a mist of perfume in a room, after some time, some people that are at the other end of the room will be able to perceive the odor. Why? Because the gaseous mist that you sprayed has now spread from your point to another point where the people are. So gases expand to fill up wherever they are placed in. They have no fixed volume applied or assigned to them. The next characteristics of gases that we want to look at is that the particles of gases move very, very fast. Okay, a gas can be at point A, let's say now, and then before you blink your eyes, it can already move to point B, because the particles that make up a gas are very fast moving. They move quickly and they move randomly in all directions, which is why if you have a gas cylinder, maybe in your kitchen, you use it for cooking, and you open it or there is a leak at some point, you notice that the gas that is coming out from the cylinder just begins to spread in all directions, and you'll be perceiving the odor from all the points in the house. That is because the particles of a gaseous substance move very fast and in all directions. The next characteristic of gases is that gases are compressible. When we say something is compressible, we mean it can be squeezed into a smaller space. You know how when you are possibly maybe moving to a new location and then you have a small Ghana must go, and then you're trying to squeeze all the clothes that you have inside it and it's looking as if it will not enter. Gases have that characteristic of being compressible. They can be squeezed into a smaller space, which is why air can be pumped into tires or gas cylinders. It is that quality of being compressible that makes it possible for us to fill up our tires with gas and our gas cylinders with our cooking gas. I hope this lesson has been educative and interesting for you. If it is, I'd like you to please hit that subscribe button, like this video, and turn on the notification bell icon. The next characteristic of gases that we want to look at is that gases exert pressure. Okay, gases exert pressure on the walls of the container that they are placed in. Now, here is what we mean. Gas particles bump into the walls of the container that they are placed in, and this creates pressure. The more of a gas we have, the higher the pressure. Now you can see on the left side of the screen over here, we have a deflated balloon, a balloon that contains basically a small amount of gas inside of it. And you can see or notice over here that the pressure on this balloon over here is very, very small, very small or negligible. However, when we begin to pump this balloon and we put in some gas particles inside, you find that the pressure begins to increase. Why? Because as more gas particles begin to enter inside this balloon, they are now exerting more pressure on the walls all around this balloon. So that is why the balloon is expanding. Why? Because the pressure inside of it is on the increase. That is because gases exert pressure upon the walls of the container that they are placed in. Now, here are some everyday examples of gases that we have and that apply to our everyday lives. Example number one: when you blow air into a balloon, okay, what happens is that the gas fills up the balloon and stretches it out. You can see in the previous slide where we saw a deflated balloon, when it was not yet blown up, the balloon was just laying down there and it was not stretched out. But the moment we began to inflate it like we have over here, you can see the balloon is beginning to get stretched out because gases are now being inserted into the balloon. So the first example we have is the example of blowing air into a balloon. The next example we have is the example that most of us can relate to: the cooking gas in our kitchen. Okay, so the cooking gas in our kitchen has a concept of something that is happening. What is happening over here? LPG, by the way, LPG stands for liquefied petroleum gas. Okay, let me just do well to spell it. Liquefied petroleum gas. That's what LPG stands for. You're welcome for the new information. So what's happening over here is that this is a gas that is stored under pressure in the gas cylinder. Okay, so that's the second example of gases that we have in our everyday life. The third example that we have is the example of opening a soda bottle. Many of you may have had this experience where you're trying to open maybe a bottle of Coke, a bottle of Fanta, and in the process of opening it, you hear this sound like ch. That is the sound of a gas escaping from that bottle, and that gas is known as carbon dioxide. When carbon dioxide escapes from your bottle of soda, it makes that ps sound. I hope this lesson is being educative for you. The next example of gases that we have are the gases that are contained in the tires of our cars that we drive every day. Now, what's happening over here is that the tires of our cars are filled with air. And air, of course, is a mixture of gases. And those gases, when they are placed into the tires of our car, they support the weight of that car. You can see that gases are so important in our everyday lives. And then one next example that we have of gases is the example of when we breathe. When you breathe in and you breathe out, you are interacting with gases through the process of respiration. For instance, I have an illustration over here of somebody breathing in. And when you breathe in, you take in a gas that is known as oxygen. Oxygen in chemistry is denoted as O2. And when you breathe out, you release a gas into the atmosphere that is known as carbon dioxide. And in chemistry, we denote carbon dioxide as CO2. So you can see gases do not just apply to chemistry laboratories, they also apply to the activities that we carry out in our daily life. So now that we've talked about some of the examples of gases in our everyday lives, let's talk about some of the basic gas terms and how they've been made simple for us to understand and grasp. So now before we move into the calculations, I know when some of you saw the intro of this video, you were thinking maybe we're going to jump into calculations and formulas and all of that. No, we're going to do that eventually, yes, but we're building this step by step into a crescendo. So we're taking everything one step and one precept after another. So let's talk about some of the basic gas terms and let's break each and every one of them down simply. The first gas term we want to talk about is the term pressure. You cannot talk about a gas successfully without talking about pressure. And when we say pressure, we're talking about the force that gas particles put on the walls of the container that they are placed in. Think of it like tiny punches coming from all directions. When you pump a tire, for example, or you pump a ball, that ball becomes harder. It becomes harder for you to, press that ball or compress it. Why? Because the gas or the air inside is putting pressure on the rubber walls. It's applying pressure on the rubber walls. So that's how the concept of pressure applies to gases in our everyday life. So now that we've talked about pressure, let's move on to the next terminology that we want to address. Now, before we do that, let's talk about some units of pressure, because when we talk about pressure, there are units that we use to measure pressure in chemistry, and the first of them is ATM. Now, when I say ATM, I'm not talking about going to the POS to withdraw cash, okay? No. In chemistry, when we say ATM, we're talking about atmosphere. And that is a unit that we use to measure pressure in chemistry, okay? And it is used basically in gas laws. And we're going to be getting into that as we proceed in this series. The next unit of measuring pressure in chemistry is pascals. Now, pascals is denoted using PA, okay? That is a short form of writing pascals. Now, in chemistry, 1 pascal or 1 atmosphere is equal to 101,325 pascals. Okay, so the next unit for measuring pressure in chemistry is millimeter mercury. Okay, mm stands for millimeter and then hg stands for mercury. Okay, so that's a unit for measuring pressure, millimeter mercury, or torr. It stands for 1 atmosphere. Over here, ATM stands for atmosphere, is equal to 760 millimeters mercury. Just like the way you have 1 kilometer is equal to 1,000 meters. The same way we have all these conversions of units. 1 atmosphere is equal to 101,325 pascals, and 1 atmosphere is equal to 760 millimeter mercury. I trust this lesson is being interactive and educative for you. Now that we've talked about pressure, the next terminology we want to talk about is the terminology called volume. Now, what is volume? In chemistry, or generally, we say volume is the space that the gas takes up. So what this means basically is the more of a gas you introduce into a place, the more space that gas will occupy. Here is a relatable example. You can see over here, this balloon is deflated. It doesn't occupy so much space. But over here, where we have more gases placed into this balloon through the process of inflation or inflating it, the balloon has now occupied more space. Why? Because more gases have been placed inside the balloon. The balloon got bigger because we blew more air into it, and the volume of gas is now increasing because we are introducing more gases into it. Now, there are some units that we use to measure volume in chemistry as well and in gas laws as well. The first of them is the unit called liter, and we denote liter in chemistry by using a capital letter L, and it is one of the most common units used for measuring volume in chemistry. The second of them is called milliliter, ml, over here, and it is called, yes, it is called milliliters. And a unit of conversion says 1 liter is equal to 1000 milliliters. I hope you're following. So if you want to convert from liters into milliliters, you multiply by 1000. And if you want to convert from milliliters to liters, you divide by 1000. The next on our list is centimeter cube. We call it basically cm cube in chemistry. Now, what this means is, or what this is called is cubic centimeters. Okay, so cubic centimeters are actually equal to milliliters. So if I say, for example, 1000 cm cube, it is basically equal to 1000 milliliters. The two units are equal to themselves. Now that we've seen some of the units of volume in chemistry, let's move on to the next terminology that we want to talk about. The next on our list is the terminology called temperature. Now, temperature simply tells us, okay, in basic science, we were told that temperature is the measure of how hot or cold an object is. In chemistry, it's no different, okay? Temperature simply tells us how hot or cold something is, and it affects how fast gas particles move. The hotter an object is, the faster its particles begin to move. And the colder an object becomes, the slower its particles begin to move. Now, why did I say that? When you boil water, for instance, the container begins to vibrate. You can see I have an illustration of of a kettle here that contains boiling water. Because of the heat that has been applied to the water, some gas particles are beginning to evaporate from the kettle, and as a result, they are beginning to make this lid, the lid of the kettle, to come off the surface of the kettle. Why? Because the gas particles that are contained inside are now vibrating, and they want to move because of the heat that has been applied to it. So when a gas particle becomes hotter, it begins to move and vibrate faster. Now, there is something important you need to know. In gas laws, whenever we're talking about the concept of gas laws, we always measure temperature using the unit of Kelvin. We do not use Celsius to measure temperature. So if you are given temperature in Celsius, degrees Celsius, when you have a gas law question to solve, you need to convert it from degrees Celsius to degree Kelvin. I hope I'm clear on that. And how do you convert? You simply add 273. So for instance, let's say you were given a temperature of 2 degrees Celsius. To convert it to Kelvin, you simply say 273 plus 2, which will give you 275 degree Kelvin. I hope we are clear on that. So now that we've talked about the terminology called temperature, the next terminology we want to talk about is the terminology called the mole. The mole is so important whenever we're talking about gas laws. And a mole is simply just a way of counting particles. For instance, when you say a dozen, we are talking about 12, the number 12. For instance, if I say, give me a dozen pencils, what I mean is give me 12 pencils. In the same way, when I say give me the mole of a substance, we are talking about 6.022 times 10 raised to power 23 particles, according to Avogadro's number. Now, here is a relatable example. In chemistry, it has been discovered that 1 mole of a gas occupies 22.4 liters or 22.4 dm cube in terms of volume at standard temperature and pressure. So now, if that is the case, and then they ask you a question saying, what is the volume that 2 moles of a gas will occupy? It is simple. If 1 mole occupies 22.4 liters, therefore 2 moles will now occupy X. If we cross multiply, this is X times 1 is equal to 22.4 times 2. X times 1 is X. 22.4 times 2 gives us 44.8 liters. So basically, that's how this concept applies to number of moles. Now that we've talked about that, let's talk about some the concept of converting units from one unit to another. So the first question we have over here is an example asking us to convert 25 degrees Celsius to Kelvin. Now, when you want to convert from degrees Celsius to degrees Kelvin, what you do is just to add 273. We saw that a few slides ago. So now we have degrees Celsius to be 25. To convert it to degree Kelvin, we simply say 273 plus 25. 5 plus 3 here gives us 8. 7 plus 2 gives us 9. And this 2 basically remains the same. So this is 298 degree Kelvin. We have converted from degrees Celsius, 25 degrees Celsius. We've converted it to degree Kelvin, which is 298 degrees Kelvin. I'm sure you saw how that was carried out. The next conversion unit we want to see is converting from milliliters all the way to liters. Now we have this question that says convert 500 milliliters to liters. So the first thing we need to know is how many liters or how many milliliters make 1 liter. 1000 milliliters make 1 liter. So if that is the case, 500 milliliters will now make X liters. At this point, we can cross multiply. If we do so, we have 1000 times X being equal to 500 times 1. 1000 times X gives us 1000X. And then 500 times 1 is basically the same, 500. To get X, we just divide both sides by 1000. This cancels this. And this is divided by 1000. This is 0.5 liters. So we have converted 500 milliliters to be 0.5 liters. We can write it like this. We can also write it like this, 0.5 L, or we can even write it like this, 0.5 dm cube. Dm cube and liters are both the same thing. So now we've converted for temperature, we've converted for volume. Let's convert for pressure as well. This question says convert 2 atmosphere to millimeter mercury. They've given us a hint at this point. They said 1 atm or 1 atmosphere is equal to 760 millimeter mercury. So if 1 atmosphere is equal to 760 millimeter mercury, 2 atmospheres now, 2 atm will now be equal to X millimeter mercury. So let's go ahead and cross multiply. If we cross multiply, this becomes X times 1 being equal to 760 times 2. X times 1 is X. 760 multiplied by 2 will give us 1520. 1520. So X is equal to 1520 millimeter mercury. We have successfully converted 2 atmospheres or 2 atm to millimeter mercury, which is 1520 millimeter mercury. I'm sure you're enjoying every bit of today's class. So having said all of that, remember this is an introductory video into the concept of gas laws. Okay, here is a quick recap table that I want you to use to remember all that we've talked about, and more like a summary. There are some terminologies you need to be familiar with when it comes to gas laws. The first is pressure. Pressure measures the force of a gas that it applies to the walls of the container that it is inside. The units that are used can be either atmosphere, pascals, or millimeter mercury. Here is a tip. The more of gas you have, the more the pressure. The next terminology is volume. Volume talks about the space that is occupied or taken by the gas in a container. The units that we use are either liters, milliliters, or centimeter cube. And the tip for this is the more volume you have, the more space that will be occupied. The next terminology is the terminology called temperature. Now, as far as temperature is concerned, it measures the heat level of a substance. And the units that we use as far as gas laws are concerned is Kelvin. We do not use degrees Celsius. This is not allowed. Okay, now here is a tip. Never use degrees Celsius in formulas. You won't get the right answer. Then the final terminology is number of moles or moles basically. This measures the amount of gas and the unit used is mole. And here is a tip. 1 mole always occupies 22.4 liters at standard temperature and pressure. I want to say a very big thank you to each and every one of you who have stuck around till the end of this video. It brings me so much pleasure to serve you with my gift potentials and all that I've got. If you stuck around till this point, I want to say a very big thank you, and I want to implore you to subscribe if you have not, so that you can enjoy more and more of these things coming from me. Up until I come your way next time, my name is David, and all I do here is to take the mystery out of chemistry so Chemi can make history. I will see you in the next video.